Albert Einstein, Niels Bohr, their names resonate through history, giants of physics. Einstein, with his theory of relativity, redefined gravity. He unveiled the universe's grand architecture. Bohr, a pioneer of quantum mechanics, explored the universe's smallest secrets. He illuminated the atom's strange and wonderful world. Their paths crossed often in the 1920s and 30s. A friendship blossomed, forged in mutual respect, yet a profound disagreement simmered beneath the surface. A clash of titans was inevitable. The arena, the baffling world of quantum mechanics. Imagine a tiny realm, smaller than atoms. Here the familiar rules of physics crumble. Particles behave strangely. They exist in blurry states of probability, not definite locations. Imagine flipping a coin. Until it lands, it's both heads and tails. This is the essence of quantum superposition. A particle's properties remain undefined until measured. This baffled many physicists, including Einstein. He found it unsettling. Could the universe be so fundamentally uncertain? He yearned for a deeper, more deterministic reality, one where particles had definite properties even when unobserved. Einstein, ever the skeptic, famously declared, "God does not play dice with the universe." This wasn't about religion, it was a profound statement about his unwavering belief in a universe governed by laws and principles that were absolute and unchanging. It was about his deep-seated belief in a universe governed by order, not chance. He envisioned a cosmos where every event, no matter how small, was determined by a set of underlying principles. He argued quantum mechanics was incomplete. To him, the theory's reliance on probability and randomness was a sign that it was missing crucial elements. Hidden variables, yet unknown, must underpin this apparent randomness. These variables, he believed, held the key to a more complete understanding of the universe. Like a cosmic puppeteer, these variables would predetermine the particles' fates. They would act behind the scenes, orchestrating the dance of particles in a deterministic manner. The illusion of chance would be lifted. The universe, in Einstein's view, was a grand clockwork, with every cog and wheel moving in perfect harmony. Einstein spent years devising thought experiments. These mental exercises were his way of probing the depths of quantum mechanics and testing its limits. He aimed to expose the flaws in quantum mechanics and reveal the underlying deterministic reality he believed in. His quest was not just a scientific endeavor but a philosophical journey to uncover the true nature of reality. Bohr, ever the pragmatist, accepted the strangeness of the quantum world. He embraced the idea that the universe at its smallest scales behaved in ways that defied classical logic and intuition. He argued that probability wasn't a sign of incomplete knowledge. Instead, it was a reflection of the inherent uncertainties that govern the quantum realm. It was a fundamental aspect of reality itself. This meant that the behavior of particles could only be described in terms of probabilities, not certainties. Particles genuinely existed in these blurry states. They didn't have definite positions or velocities until they were observed. Only upon measurement did they choose a definite state. This phenomenon, known as wave function collapse, was central to Bohr's interpretation. This wasn't about limitations in our ability to measure, it was about the intrinsic nature of quantum systems. It was about the very nature of reality at the quantum level. Bohr's ideas challenged the very foundations of how we understood the universe. Bohr argued that our classical intuitions, honed by experiences in the macroscopic world, simply don't apply in the quantum realm. The rules were different and we had to adapt our thinking. We had to expand our understanding of reality. This new perspective opened up a world of possibilities and fundamentally changed the course of modern physics. Their debates were legendary. Passionate yet respectful, they embodied the spirit of scientific inquiry. These discussions were not just about theories but about the very nature of reality itself. One such clash revolved around the EPR paradox, a thought experiment devised by Einstein and colleagues to challenge the foundations of quantum mechanics. This paradox questioned the completeness of quantum theory. It involved entangled particles, which are linked in such a way that measuring one instantly affected the other, even across vast distances. This phenomenon seemed to defy the principles of locality. Einstein saw this spooky action at a distance as proof that quantum mechanics was flawed. He believed that there must be hidden variables that quantum mechanics failed to account for. Bohr countered that the entangled particles were part of a single holistic system. He argued that quantum mechanics was complete and that the paradox highlighted the need to rethink classical concepts. Their fates were intertwined, regardless of distance. This entanglement suggested a deeper, more interconnected reality than previously imagined. The debate raged on, unresolved. It was a clash of titans, each pushing the boundaries of human understanding. Yet it pushed both men to refine their arguments, to probe deeper into the heart of reality. Their intellectual duel was a catalyst for progress in physics. The impact of their clash of titans continues to reverberate through the scientific community. Their debates have inspired generations of physicists. It spurred technological advances from lasers to transistors and laid the groundwork for modern quantum technologies. More importantly, it ignited a philosophical firestorm about the nature of reality, determinism, and the limits of human knowledge. The implications of their debates extend beyond physics. The game of dice continues as scientists and philosophers alike grapple with the mysteries of the quantum world.